Hello everybody, thank you for being here today. Grab your notebook, grab graph paper, preferably a graph notebook, and go ahead and please label that from -1 to 1 on the x-axis, and from 1 to 3 on the y-axis. Today we're going to be doing a problem from slope fields. This is math from the void. Math coming at you out of nowhere. And today we have a problem from the 1998 AP Calculus BC exam. Stick around long enough, we might get something from this century. Maybe. They'll be coming around. So in this slope fields problem, they specify 9 points. See these 9 points that I've emphasized, between -1 and 1, and between 1 and 3 on the y. They want us to just sketch the slope field for this differential equation at the 9 points indicated. If you can't read what that differential equation is, my apologies. This is dy dx equals xy over 2. And something important about this, we know that this is going to equal 0. It's never going to be undefined, but it's going to equal 0 if x equals 0 or if y equals 0. Now, x equals 0 is the only thing that we can see on this because y equals 0 is right here. We're not counting that. So already we have some flat slopes here, here, here. Notice that if x and y get bigger, like if x gets bigger, the slope gets bigger. And if y gets bigger, the slope also gets bigger. So we should expect this to have kind of a positive 1 times 1 over 2, maybe like that. And then here we have positive 1 times 2 over 2, which is just a slope of 1. At 1 comma 3, we have a slope of 3 over 2, so maybe just a little bit steeper than 1. Now, if x is negative but y is positive, it's going to have the same values, but they're just going to be negative slopes. So this would be a slight negative slope, a negative slope of 1, and then a little bit steeper of a slope. Okay, that looks about right. So there's our slope field complete. Part B says let f of x be the particular solution to the differential equation. So we need an initial condition. There we have it, f of 0 equals 3. We have to use Euler's method. This is a very specific method of using the tangent line, but then kind of adjusting your tangent line approximation as we go. And it tells us the step size. So it tells you when you're going to reset. You're going to reset your slope after a step size of 0.1, and we're going to approximate f of 0.2. So we're going to take 2 steps along the slope field, in a sense, in order to approximate what f of 0.2 is. All right, so let's just emphasize that f of 0 equals 3. Now the tangent line at that point is going to look like this. Y minus 3 equals f prime of 0 times x minus 0. So in other words, y is approximately equal to f prime 0 times x plus 3. Well, f prime of 0, if we want to approximate 0.1, it's going to be approximately f prime of 0 times 0.1 plus 3. But f prime of 0, that means x equals 0. That's going to give us a slope of 0. So our f of 0.1 is actually still 3. That's kind of weird. We didn't make any progress, but that's because if you look at the slope field is 0 at that spot. So it's telling us that if we follow the tangent line there, of course, we're just going to stay flat for a minute. And that's why Euler's method is effective, because if there's a flat point, we'll go along the flat slope for a while, but then we'll pick up on the correct slope once we progress forward a little bit. So we're going to make a change in our slope, and that's going to give us a closer approximation. Let's do the next step. So the slope of the tangent line here at the point when at the point 0.1 comma 3, we say it's approximately 3. That tangent line is going to look a little different. It's going to be y minus 3 equals f prime of 0.1 now times x minus 0.1. Okay, so if we're trying to approximate f of 0.2, that's going to be the derivative at 0.1 times 0.2 minus 0.1, which is also just 0.1, plus 3. Okay, well, what is the derivative at 0.1? Let's take a look at the differential equation. It tells us that the slope is equal to the x value, 0.1, times the y value, which is 3, over 2, which is 0.3 over 2, which is 0.15. So our f of 0.2 is approximately 0.15 times 0.1 plus 3. So that gives us 3.015. That is our approximation for f of 0.2. Okay, so we used the slope field to say, well, we know that there's a point here, and that means that there would be a flat slope, so we're just going to go along that flat slope for a little spot. And then we stop at 0.1 and say, wait, what's the slope here at 0.1? Because now I kind of want to travel more accurately to the graph at that point. And they say, oh, the slope is very small, it's 0.15. So we say, okay, let's travel 0.15 slope. Of course, I'm exaggerating it, that's more than 0.15 slope. But the idea is that it allows us to shape the curve just a little bit, and our approximation will be close as possible to the true function value. Part C, speaking of that, part C has us solve the differential equation. Find the particular solution is the same as telling us to solve. Find the solution means to solve it, right? Find the solution to the differential equation with that initial condition f0 equals 3, and then use your solution to find the true value f of 0.2. So let's separate this equation first. Let's separate the differential equation. We got to get all the x stuff on one side and all the y stuff on the other side. So we're going to multiply dx dx. So now we have dy equals x over 2 times y dx. So now let's divide both sides by y. And we'll have 1 over y dy equals, I guess, 1 over 2x dx. Now we're ready to integrate. Ready? Go ahead and integrate. This is going to leave us with ln of absolute value of y equals x squared over 4 now. This is the power rule. Raise the power by 1, divide by the new power. Plus c. Well, we can find that plus c because we were given the initial condition, right? Let's go ahead and do that. Well, if we plug in 3, use 0, 3. If we plug in 3, that's ln of 3 equals 0 squared is 0 over 4 plus c. So that means c is equal to ln of 3. And that's going to be helpful because we want to change this into just y equals by raising everything to the e, or to a power of e. X squared over 4 plus ln of 3. Well, that's just going to turn this into 3 times e to the x squared over 4. If you don't understand why, I'll walk through it this one time. Don't get used to this. When I'm adding exponents, that's the same as multiplying by the same base. So e to the ln of 3 times e to the x squared over 4. E to the ln of 3 is just 3, so this is 3 times e to the x squared over 4. Okay, that's some pre-calculus stuff that like you gotta be comfortable with. So here's our equation, and they want us to use this equation to approximate what f of 0.2 would be. Is it 0.2 or 0.02? Yeah, 0.2. Okay, 0.2. Got it. So that is going to be exactly equal to 3e to the 0.2 squared over 4. That's kind of weird. Which is 3e to the 0.04 over 4, or in other words, e to the 0.01. That's really close to 0, but it's not quite. So I would leave my answer like this. I don't think this was a calculator problem. If it is, go ahead and use it, but I don't think it was a calculator problem. You'd probably get like 3.05 or something really small. It'd be something really, really small. But I wouldn't even write that. I would leave it like this, because if you try to approximate it and then you're wrong, first of all, they might be like, what are you doing? Like, do you have a calculator? Are you cheating? But second of all, they might say, no, this was more accurate to begin with, and then you made it less accurate by trying to guess what the value was. So that covers the tedious topic of slope fields. We didn't have to do a whole lot with that slope field, but largely we'll have to use the slope fields to solve a differential equation. All right, that should do it from here. I'll see you next time in the void.